We'll do one more example that comes from an applied problem and builds up the eigenvalue problem or the linear systems problem that we were working with last time. Example 2.2.5. We'll actually do two more examples, to be honest with you. All right, so do you remember we had the t equals 0 case, which was associated, do you remember what we called this entire apparatus that I brought in last time? Mass spring, chain. Why was it called a chain again? Because it was linked together. We had masses and springs that were linked together. So we call that M1. We have another one called M2 all the way down here. We marked, do you remember what we did to start this one? Yeah, we marked the center of mass under equilibrium. So gravity was turned off, no motion, no net force. And we said that this was going to be x1, x2. And we could also say this is x1 of 0, x2 of 0. So at the initial time that I started, right? And then what did we do?
Turn gravity back.
Yeah, and I'm going to go ahead and encourage us to think about turning gravity back on as allowing time to elapse. The reason that I'm going to allow time to elapse is I want to derive it in the general, drop down to the specific for our linear systems problems that we're going to do, but keep in mind that this can be a dynamical system. Meaning that the masses could be moving, and at any point t, we're going to track the center of mass. Could you guess what we're going to call it? x1 of t, lowercase t, right? Meaning to say that the position is a function, not a scalar. So it doesn't necessarily have to be an algebraic problem. We will definitely study the algebraic problem, and we will use linear algebra to do so. But we will also study the differential problem, and we will see how to transform the differential problem into an algebraic problem using linear algebra, known as eigenvalue theory. So from this standpoint, what did we do in that second one? Yeah, we're not ready for the displacement yet. But what we said is, the first thing we're going to do is turn gravity off, let the thing settle down in equilibrium, let it stop, let it be 0 velocity, 0 acceleration, 0 net force, and then track the center of mass along my ruler. Then what was the next thing that we did? Turn gravity on, or more specifically, let the masses move, and then just track the position of the center of mass along the ruler, and then call the position of the center of mass at any time t. So the position of center of mass 1 at any time t is x1 of t. The position of center of mass 2 at any time t is x2 of t. All right. And then what you all are saying to me is that we can actually track the change in these positions. So we can look at the change in the initial positions here. And what would a physicist call change in position? Displacement. And maybe we want to use u1 of t and u2 of t. Go ahead.
Are we tracking displacement at any given point in time, or when the thing finally reaches equilibrium?
Yes. We are tracking displacement at any point in time. And for the linear systems problem, we will make sure that it settles down into equilibrium. If we track it at any point in time, that's called an eigenvalue problem. If we force it to settle down into equilibrium, that's called a linear systems problem. One is the domain of a dynamics class. The other is the domain of a statics class. Right? Yep.
And the capital T represent any point in time?
Capital T represents the end point of my experiment. In the case that Joe was just mentioning, where we turn gravity on, let it settle to equilibrium, and measure the final resting place, then capital T would represent the moment at which those masses settle down under the force of gravity. If I'm in an eigenvalue problem and I'm analyzing the motion of the masses over time, capital T would mean the end of the period that I care about. If I'm somebody that's working on a car suspension system, that might be if I do a Dirac delta function shock, aka if I go over a pothole, my capital T might be the amount of time, a little bit more than the amount of time that the car takes to settle back down into stable equilibrium, right? if I'm working on a building analysis problem, so an earthquake shakes the building, could you guess what my capital T might be? Probably a few minutes after the end of the shaking. So I could actually talk to people that study earthquakes for their life and say, how long is an average earthquake? How long is the longest earthquake that's ever been recorded on human history? And then I could say, oh, why don't I just put my T to be 5 minutes after that? How long did that happen? Okay, so let me ask you this. Could you imagine what we'd say x0 is? Yeah, so if we think about x0 as the 0 position, so what would the vector x0 be? It would be the vector of equilibrium positions, the initial positions of the masses, right? Could you imagine what x of t is? Yeah, it would be a vector valued function whose individual entries would store, whose ith entry, so what would the first entry store? The center of mass 1 at any point t. What would x2 of t store? The center of mass 2 at any point t. How might you define u of t? Well, let's do the component definition of u of t. What's the first component of u of t? u1 of t. And what would u1 of t be? What would it track? Oh yeah, you're a little bit faster than old Anderson. So you said this would probably be x1 of t minus x1. What about the second component? x2 of t minus x2. Could you write that as a vector subtraction problem? Could you guess what vector subtraction is? So I guess I got to write it like this. So formally speaking, I have that, right? Yeah, so now I've got, this is now x1 of t, x2 of t, plus a minus 1 times x1, x2. And then, could you guess what we say about plus a minus? Same thing as a minus. So we would say that this is x of t minus x naught. Or you could say plus a minus 1 times x naught. That's scalar vector multiplication. That's vector-vector addition. And we can say, oh, those with our powers combined, we are vector subtraction. Right? Which is the same thing that we saw back in the real number system, which kind of gives us hope, right? Because these are all just a bunch of real number operations underneath. Okay, so this is a way that both scalar vector multiplication and vector-vector addition show up in a practical problem.